Hey everyone, welcome back. So today we're going to be talking about how molecules interact with each other. And to do that, we need to cover an important concept: polar and non-polar covalent bonds. Polar and non-polar covalent bonds. So what do I mean by this? Polar and non-polar. So let's talk about the polarity in covalent bonds. So picture this. Atoms are like roommates sharing an apartment. In a covalent bond, they share electrons, but not always equally. Imagine one roommate hogging the couch a bit more. This creates a partial negative charge on their side. The other roommate, left with less couch space, becomes slightly positive. This uneven sharing of electrons is what we call polarity. Take water for example. The oxygen atom is a couch hog, pulling electrons closer, making it partially negative. Hydrogen atoms get less couch space and turn partially positive. This polarity is why water molecules stick together, making drops and allowing life to thrive. So that's just a simple explanation of polarity. So let's get more into it. So let me give an example of that. Let's say we have oxygen, an oxygen atom. I'm just drawing the valence shell for simplicity's sake, right? An oxygen atom, you might recall, has 6 electrons in its valence shell. So how does it get its remaining electrons? By sharing them with hydrogen, correct? So let's draw a hydrogen atom sharing these electrons with the oxygen. Now if you look at it, you might realize that oxygen, right? Oxygen, to be stable, to be not stable but to be a non-charged particle, right, needs to have 8 electrons in total, which means 6 in its valence shell. But in this case, you've added 2 electrons to its valence shell. So even though that you still have the hydrogen that might cancel some things out, you have what you call a partial charge. So oxygen has more electrons, so it has a partially negative charge, right? It has a partially, that's a symbol for partial, negative charge. And each of the hydrogens have a partially positive charge. So this is what you call a polar molecule. Polar molecules form when you have these partial charges. These partial charges are going to be there no matter what type of covalent bond you have. But the thing is about the symmetry of the bond, right? So here's the symbol that you draw. So, or before I go for that, let's just talk about the symmetry of the bonds, okay? So what do I mean by saying that H2O water is asymmetrical? Well, let me give an example of a symmetrical bond, alright? CO2, you might recall, is carbon dioxide, right? So let me draw the picture for that. So you have carbon. Carbon has how many? Carbon is number 6, which means it has 6 minus 2, 4 electrons in its valence shell. 4 electrons in its valence shell. What does that mean? It needs 4 more electrons to be happy, right? So what happens? Now comes along oxygen and says, okay, so there's 2 of me, 2 oxygens. We each need 2. We each need 2 more to be happy. And we'll give you 2 each to be happy. Okay? So what happens is, in total, carbon gets its 8 bonds. And oxygen also gets its 8 bonds. So what happens? This forms carbon dioxide. So the way you write these bonds, I'll just say that, is you have the name of the element, the shape of the molecule, and the number of electrons that the joining molecules give. So hydrogen each gives 1, so you just draw one line like that. Oxygen and carbon each share 2, so 2. So this is called a double covalent bond. This is a single covalent bond. Depends on how many electrons are shared. So if you look at the structure of this, right, each of these oxygens are also partially negative, and this is partially positive. But you'll realize that there's equal number of partial negativity here as there is here. And so what happens when you're trying to go both ways? They just cancel each other out. And so in total, this carbon has no charge. Right? Absolutely no charge. However, when you look at oxygen, right, both of these are not going in opposite directions. In fact, they're both tending to lean towards the same direction. So this is what we call the asymmetry of the molecule. If the molecule does not have equal symmetry like this and is asymmetric, then it forms a polar covalent bond. This is what we call a polar covalent bond, and CO2 would be a non-polar covalent bond, no charges. Okay, hope you've understood this. If you haven't, please rewatch or do some research of your own. It's important to understand the next concept. Next concept we're going to talk about is molecular interactions. Okay, so there are a few types of molecular interactions that can occur. First, let's talk about those in non-polar covalent bonds. Non-polar covalent bonds are, first, what do I mean by molecular interactions? And let's say you have a bunch of molecules put into a box. Okay, let's have a box like this. Let's have a bunch of molecules here. It's how do these molecules interact with each other? Are some of them attracted to each other? Are some of them repelled from each other? What's the difference, right? What happens? So that's where we get to molecular interactions. So to be attracted or repelled, what do you need? You need to be an opposite or the same charge, correct? So you might be wondering, how do non-polar covalent bonds have molecular interactions? They're a neutral charge, right? None of them have a charge, then they can't interact with each other in any way. However, there is something that we call a London dispersion force. London dispersion does not mean the London Bridge is falling down. It's just a name of the weakest type of molecular interaction. It is the weakest type of molecular interaction. What do I mean? What happens? Well, in non-polar covalent bonds, the thing is, sometimes electrons can shift a bit this way or shift a bit that way. And that slightly creates partial charges. It's extremely weird. It will never happen in real life, but that's just how it is. So, let's say you have the same drawing, CO2. Sometimes in this overall molecule, the charge can slightly shift this way to become partially negative. So what then happens? And some in another CO2 molecule, the charge can slightly shift some way become partially positive or something, or the charges slightly shift, what happens? These two will then attract each other. If this becomes negative, then these two will repel each other, right? So that's what London dispersion forces are. Let's talk about what happens in polar covalent bonds. Polar covalent bonds are what we call dipole-dipole interaction. What is a dipole? Well, a dipole is what is formed when you have the partial positive and partial negative ends of the atom, right? What happens is they attract each other. So if you have a partial negative end, that's going to be attracted to the partial positive end, and it's going to go like that. So that's the dipole-dipole interaction, where you have some polar covalent bond molecule and another polar covalent bond molecule, and so let's say this is the partial negative end, this is the partial positive end. These are going to be attracted, and the partial negative end is going to be repelled by the partial negative end here. These are attracted, these are repelled, and that's what creates the forces. These are stronger than these, but just a little stronger. Okay? Weakest, little stronger. Then we come to the strongest form. They're called hydrogen bonds. These are the strongest type of molecular interaction. Hydrogen bonds occur when you have a polar covalent bond that has a hydrogen atom. But not just any polar covalent bond. It has to be either nitrogen, oxygen, or fluorine. These are the chemical symbols for those three elements. If one of these three elements forms a bond with hydrogen, let's say NH3, H2O, or FH, right? What's going to happen? HF, thank you. What's going to happen? These are going to have hydrogen bonds within them. Let me explain in an easy example. It's pretty much the same thing as a dipole-dipole interaction, but it is stronger because of hydrogen. So you have oxygen here that's tied to two hydrogens, right? The hydrogens are all partially positive and the oxygen is partially negative. Let's say you have another partially negative oxygen with two hydrogens, another partially negative oxygen with two hydrogens, right? So what happens is the partially positive hydrogen, partially negative oxygen are attracted to each other. They form bonds. They're not as strong as covalent or ionic bonds. They're not like firm gripping bonds, right? But the attraction is high enough that they tend to stick together. So that is what hydrogen bonds are, and that is what, and these molecular interactions, right, they play a key role in many instances. So let's look at a simple one, surface tension. What do I mean? Might have noticed that sometimes when you drop a drop of water, that the water kind of bubbles up like this, right? Why does it form a bubble like that? Well, that is because of, in this case, one of these three hydrogen bonds, right? So if you look at that, at the top, all the other, let's just say that's a water molecule, right? All these other water molecules are held together by hydrogen bonds, right? So they're held together in all directions. However, the ones on the edge are only held together from the back. And they have nothing above them that holds them together. So these ones right here on the edge, they're like kind of tied together and held back. So they compress on the liquid themselves to form a clear layer. And that's what forms this bubble. And the tension that's in between these top layers, what we call as surface tension. And so this surface tension exists in all liquids, and depending on the strength of these bonds, it will change in how strong the surface tension is. There's another property called viscosity. So let's write that down. Surface tension, then viscosity. Not sure if that's how you spell it. You might want to check on that. But anyways, how viscous a substance is, right? What do I mean by that? You might have noticed that if you have a jar of honey, to like swirl honey around is much harder than if you're just swirling regular water around, right? Well, why is that? Why is honey so much more thicker, so much more viscous, has a higher viscosity than water? Well, that's because it has stronger molecular interactions. Stronger molecular interactions bind the molecules together more, so it's harder to move them around and change them. So this is just the basic molecular interactions and polar, non-polar covalent bonds. These will be used and seen in many other instances. If you're just from boiling different substances to doing all sorts of experiments with them, you'll need to make sure that you know the strength of their bonds, and that will change the amount of energy you need to use to do something with it. So make sure that you know all these well. Thank you very much for listening, and continue learning like always. Thank you.